So if you just remember previous lecture, in previous lecture we had discussed about the hard margin SVM. Means what? Hard margin SVM means we have our taken data set is linearly separable or it is almost linearly separable. There we have not considered any misclassified point. But in soft margin SVM, we are considering outliers as well as our misclassified point. So let's see what changes happen in our optimal equations. Okay, so first redraw our equations. So for pi plus planes I am using the blue ink as usual. Okay, this is our pi plus plane, and what be our these equations of our pi plus plane. These equations is W transpose xi plus b is equals to 1 for our pi plus plane. And let's take using red color for our pi minus plane. This is simple our pi minus plane. And what be our equations of pi minus, that is W transpose xi plus b is equals to -1. Okay, and let's take our main optimal plane is pi. This is our pi plane. And what be these equations, that is W transpose xi plus b is equals to 0. These equations. So these are our three planes. So now let's take the points. Suppose I am simple as usual, I am using the blue ink for our positive points. And for this blue ink for positive points, yi value always is +1. And I am using the rating for negative points. And yi value for these negative points also -1. So first put our support vectors. Let's take this is one our support vectors. One, just I am for clear pictures I am taking here less amount of data because you can understand this thing easily. And this is our positive support vectors, and let's take here is our negative support vector. This is our negative support vector. Okay, and this point and this kind of points is our positive non-support vectors. That's this one, our these kind of points are and positive non-support vectors, and these ones are our negative non-support vector. And as well here simple here I am using the positive misclassified point. If we are simply understand the calculations of positive misclassified point, then I think you can easily understand the same calculations of negative misclassified point, how to handle this. So just in these pictures I am considering the positive misclassified point. Okay, the same concept is applicable also negative misclassified point. So positive misclassified, I am taking one point here. This one is the first misclassified point. Just I am using the circle. And these guys, if I taking point here, these guys is also another misclassified point. And if I taking one point is just take here is our one point. These guys is also another positive misclassified point. So these three things, so just I am renaming this x1, x2 and x3. x1 is the first misclassified point, x2 is the second misclassified point, and x3 is our third misclassified point, and all the points are positive. Okay, now let's take the situations one by one. Okay, first draw one thing, and this is our normal vector w. So this is our normal perpendicular to our plane, that is w, and also w is not a unit vector. So norm of w is not is equals to 1. Simple. This is our assumption, SVM. And since pi plus and pi minus is parallel to our plane pi, then W is also normal to pi plus, and also it is normal to our pi minus, and directions always same. Directions is the same directions of. Okay. So first, just if you see this x1 point, so first let's take. I'm discussing this three type in as case 1, case 2, case 3. So first read out case 1. Case 1. I am in case 1. I am considering for x1 point. So if you just see this thing here, let's take the distance of the point from here to here. Let's take this distance is, let's take this distance is 0.5. Okay, let's take. So first, if this distance is 0.5 and this point x1 point is the positive direction, actually this is our pi plane, and this direction is our positive point directions, and this directions is our negative point directions. If you see, the x1 point lies on our positive point directions and at the same directions of W. So what will be now value of here for this point? What will be the value of W transpose xi plus b? What will be the value here in for x1 point? This value will be greater than 0.5. Obviously this thing is equals to positive, because the directions of the W and the directions of the plane from the plane pi, directions of the W and directions of the point x1 from the plane pi is the same direction. So this will plus, and this thing will be 0.5. So now I am interested to calculate it, yi into W transpose xi plus b. This thing for this point y, this is positive points, and for all positive points yi is equals to plus 1. So plus 1 into, so sorry one thing, this is not greater than, this thing is equals to 4.5. This thing will be is equals to 0.5, sorry for that. So 0.5. So this multiplication is 0.5. I am simply rewrite these equations as this. Now just see this value. Okay, now just I am just in pink color, I am just using this circle. Just see this value. Okay, so for this point, so I'm just first calculating every for x1, x2, x3. This that is calculated first for x1, x2, x3 yi into W transpose xi plus b. Then I am discussing what is the importance of this value. Okay, so first let's calculate it one by one. So in case 1, I think it is clear how we got this value. Now let's take case 2. In case 2, here I am considering the x2 point. So I am just taking this point also 0.5 from our plane pi. So distance from plane pi is 0.5. Let's take. For point x2. So now what will be the equations? What will be the value for x2? Let's first calculate the value of W transpose xi plus b equals to what? This will be equals to minus 0.5. Or why this is minus 0.5? Because the directions of the s2, if you see the directions of the x2 is in the directions of the negative set of data points, but directions of the W is the positive directions of the positive set of data points. The directions of this point and the directions of the w is opposite, so this value will be minus. Okay, and this distance is from this plane is 0.5, so it is simply minus 0.5. Okay, I think this thing is clear, all of you. I'm again and again, many times I'm using this concept. This is the same concept for every point. Okay, now I'm just interesting this calculated this point, this value. I'm just interested to calculate it now, this value w transpose xi plus b. So this is a simply this x2 point is also x2 point is also positive points, and here yi value will be what, plus 1, and this value is equals to minus 0.5. Now what is this, minus 0.5. Now I'm just rewrite these equations as this. Okay, 1 minus 1.5. Here I am writing this equation. Just I am just similarly I'm giving the pink circle mark here. This point I am giving the pink circle mark because this is the important to calculate it. Now let's consider the case 2. That is in case, sorry, case 3. In case 3 I am considering this point, x3 point. So case 3 here for point x3. Okay, now let's first take this distance from this plane to this point. At this distance is, first let's take this distance from this point to the, this is 1 because this is the minus 1, for this is the 1, and let's take this is the 0.5. So total distance let's take is equals to 1. Let's take this total distance will be 1.5. First from this plane to this distance is 1, and from here to this point is 0.5. So total from the pi plane to this point will be 1.5. So at similar case 2, this value also be at similar case 2, this value will be minus 1.5. So if we calculate it, yi into w transpose xi plus b, then this value will be for y is equals to plus 1 because this is a positive point, and it is the minus 1.5 because this is a misclassified point. It is simple. And I am just writing this thing as this. 1 minus 2.5. Now I'm just using the circle because this is the important. If you just noted, if we just denoted this thing as zeta I, of zeta I, if you just denoted this thing as zeta I, so if you just denoted the zeta I, so first this thing will be zeta 1. Let's take this is zeta 1 hour. Let's take for x2 point this is zeta 2, and this point is zeta 3. Okay, simple. For different point I'm taking the different zeta 1. So just if you see this thing, if I am just compare this thing, if you simply, if you just I am compare this thing to the distance from the this, just it is not actually distance from the point pi plus. I'm just comparing this zeta 1 from this point. For this point I'm just comparing, if you just see, I'm comparing this distance is zeta 1. I'm comparing this point to this point, this plane to zeta 2, and I'm comparing this point, this to come to this. is equals to zeta 3. Okay, just I am comparing these three things, zeta 1, zeta 2 and zeta 3, this one. So here zeta value is what? 0.5. Zeta 2 value is what? 1.5. Zeta 3 value is what? 2.5. I think you understand how this value coming. So simply this distance is 1 and this is the middle of this between two this point, so this value is 0.5. and zeta 2, if you see this distance is 1 and this is the this distance 0.5, so the total distance of zeta 2 is equals to 1.5. and this for this point this distance is 1 and this distance is 1, so total 2, and this distance is 0.5, total is equals to 2.5. Okay, I think so I think now concept of zeta 1, how it is important, it is clear. Simple, zeta means it is equal to some unit of distance. Okay, so this distance means it is equal to some unit distance of zeta. Okay, so now just take the relations, how it actually, if you see, this is pi plus is the correct classified plane for our positive points. And if we just move further and further from our positive pi plus plane, then the zeta value is increased. Okay, this is the simple concept of misclassified point. I'm using here simple this concept. Okay, if we have if our data points are misclassified, simply if you, for each case, for each misclassified, you see this, for each classified point, if you see the zeta value is greater than is equals to 0, greater than 0. If it is zeta is equals to 0, then it will be the support vectors. So we are not interested here classified point, we are interested to misclassified point. So for the misclassified point, that is x1, x2, x3, so zeta i's value is greater than 0. Okay, so just write down this thing. If just write down, if our zeta is values increased, that implies what? That implies our points are further away, sorry, not far away, that is points are far away from the correct hyperplane to the incorrect directions. Huh? Okay, I think this is the main thing. Just see this picture, then this definition will be clear, all of you. Just see this. X1 is the closest misclassified point, x2 is the second closest misclassified point, and x3 is the third closest misclassified point. So for x1 zeta 1 value is 0.5, for x2 zeta 2 value is 1.5, for x3 zeta 3's value is 2.5. So as zeta's value increases, so the misclassified point moves further away to our correct hyperplane in the incorrect direction. Okay, simple, here we are using this trick. Just one thing I am just discuss it. If we consider the correct point, then what will be the value of the zetas? Now let's see what will be the value. Suppose to denoted I am using here different color. Just I am taking here suppose this color. Here I am taking here this color. So let's consider I am using this point. This is a correct classified point, this point. Suppose let's take, I am using this correct classified point as x dash. Let's take I am here using the point was x dash, I am taking here x dash. So for this point, if the distance from the pi, if this distance from our plane pi plus, if this distance is, suppose let's take this distance is 5. So now what will be the value of now yi, we are interested to calculate it. So just write this thing in this thing. I'm just calculated this thing in this thing. Okay, so what now I'm calculating yi into w transpose xi not just here, it will be x dash plus b. So what, it is a positive point, so yi will plus 1. And now this value, because the directions of the w at the directions of the plane from our correct classified plane pi plus in the same directions, so this value will be simply positive. And what will be the value, this will be these directions, so this value will be 5 and this equals to 5. Now if I just rewrite these equations as this, so this will be 1 minus of 4. So just see this value, I am just taking this value for every point. This is called zeta is, so this will be here zeta dash. So here this zeta dash is what, here zeta dash is negative. Just I think you are understanding. If our data is proper correctly classified, then our zeta is negative. So here simply here zeta is negative, less than 0. Zeta is less than 0. So I am not interested to take in our calculation this point. This is always correctly classified. I am just interested to take this point, this misclassified. So for all misclassified point, we have see that one thing, it is increased and this data is greater than 0 for misclassified point. If I am doing some misspelling some word, just correct it. Okay, I think the spelling is okay. Misclassified, okay, for misclassified one. Okay, this is for misclassified. Okay, now I'm just write this thing. I'm just going to write the thing with what is the relations of xi and zeta in mathematical way. I'm just going to write this thing, the relations of xi and zeta is. Okay, so first, if our, we see that if our zeta is equals to 0, zeta is equals to 0 if okay, first we have taken if zeta is equals to 0, then our point is, then our point will be correctly classified, means this side of the plane. Just I am avoiding this thing zeta is less than 0. Just I am taking here zeta is equals to 0. I am avoiding this point, avoiding this is the trivial, this is properly, this is the trivial case, this is the properly classified. Okay, I am just here in this point, I am not considering the zeta's value. Okay, I'm just considering the zeta's values from negative plus only. So if zeta is equals to 0 and if w transpose xi plus yi, sorry, transpose xi plus b, and this is equals to 1, then this thing we have seen, then what happened? Then these our points are correctly classified, correctly classified as per pi plus and pi minus. So I am not taking the calculations of pi minus because the positive point calculations and the negative point the calculation are the both are the same. Okay, just I am here considering only positive point calculations. If you are interested, then as homework you can do in home, do your home for the negative calculations as well. Okay, I'm just going to calculate it. So if these situations we have seen in hard margin, okay, these situations in constant, if you just remember, if you just revisit our first hard margin SVM, then you can see this constant equation, or this is called our hard margin equation. These situations we have got in hard margin situation. This is our hard margin. This is our hard margin SVM. Now in here we got that, here we got if zeta I is greater than 0, okay, then if a zeta is greater than, then we got, then what we got, then greater than 0, then this zeta I, then this zeta I is equal to some unit of distance. Distance away from the correct hyperplane that is pi plus and pi minus. This is our correct hyperplane in incorrect direction. In incorrect direction, just see this thing. So this thing is our soft SPM. This thing, this we have seen this thing in hard margin. This thing, if we included this thing, if we included in these equations, then these equations will come into our soft margin SPM. So before writing the soft margin equation, I'm just want to see you the one formula. Already in previous lecture I am also discussed it, but I am also revisit this. So if we have a formula like this, if we have a just write for every optimal equations we have to find, just see these equations, we have to find the optimal x star, that is if this one is our arc max of f of x. This kind of equations we have seen many times, and this kind of equations, this is x star, this is same of what, these equations is same of arc mean of, if we just taking the inverse of this function, these equations as these equations both the same thing, but we are written these equations in different form, different way, but actually these things are the same. Okay, so now using this formula I am just converting these equations, maximum equations to the minimum form. Okay, Just if you remember our hard margin equation, just I am again writing our hard margin equation. Okay, just I'm just not writing here simply the constant term. Okay, in the main soft margin equation I'm including the constant term. Here just I'm just simply using this thing. Have to taking the inverse. That is simple this thing. Okay, now I am writing the our main soft margin equation. Okay, so our soft margin now equations will be, we are interested to calculate W star and B star, that is arc mean of over all W and B, norm W by 2 plus what, plus one thing. Here we are interested to minimize this zeta. If we have see that if zeta increased, there the chance of the misclassified point which increased, because if zeta increased then points are far away from the correct hyperplane in the incorrect directions. So we are interested to minimize the error. Okay, so simply just before writing this, just write this here. Here we are interested to here we are interested for what, or we have to interest or minimize the error. This implies me to what, we have to minimize our misclassified point. If we minimize our misclassified, then our the error will be minimized. Minimize the points. Simple. This thing implies that we have to, if we minimize the misclassified point, then we are interested to minimize this value. If this value tends to 0, then all our data points are appropriately classified. If these zeta values are greater than 0, then we have seen that these points are misclassified. Now we are interested to minimize this. Just we are interested to minimize these zeta's values. But we are interested to minimize this zeta is values, where I is equals to 1 to n. N means our number of data points in our training data sets. Okay, we are interested to minimize this. In another language, we call that we are interested to minimize of the average value of this. Just I am included this term here. Here I am included this term, that is 1 by n zeta is. And one thing we have to control our bias variant trait of, we have included one term C. Okay, this is our hyperparameter. How to control our, just we will see it, how to control our trait between bias and variance to controlling the value of C. Okay, so let's see. So here just this term is the, and simple, this is our what, this is this thing, this total thing is our optimal equation. This is our objective function. Objective, this is our objective functions. Now we are interested in writing constant. So what will be our constant? It's simply easy. First write down the constant for hard margin classified point. So for hard margin classified, we see that this equals to +1. Now here we are simply included one term, that is zeta I. Just see these equations. Here all the equations for misclassified equations, we are included zetas. Okay. So just here we are included here minus zeta I. Okay. So here I am just included the minus zeta i's for all I. Okay, for all I. So this will be our n constant. And what will be the value? And our zeta i's are greater than is equals to 0. This thing we have to remember. Okay, here for if our zeta is 0, then it is correctly classified. If it is incorrectly classified, then zeta is our greater than 0. So I'm just what I'm seeing, if zeta is equals to 0, that means this is our correctly classified. If zeta is greater than 0, this means incorrectly classified. Okay, this is our simple constant equations. Now if you just see this thing, I'm just going to start this thing. If you just see this thing, and if you just see this thing, so this thing, if you just see, this is our loss actually. Just we are interest to minimizing our loss. If this increased, our classification, our technique is reduced, our accuracy of our classification technique. So this is simple, we call this is our loss function. This thing we call our loss, and this is our hyperparameter. Meter, and this thing, that is norm W by 2. This is similarly we call this term as regularizer. Okay, this thing is our regularizer. And this loss function, if you see these loss functions, is just simply a average distance. These loss functions is simply the average distance of the misclassified point from the correct place. This distance, this one is the average. This point is the average distance of misclassified points from the correct pies. Correct pies means what? Pi plus and pi minus. These one are our correct pies. This is the simple average distance misclassified. So okay, till now Yeah, all the concept is clear. So here just to see, and just I am just to see this thing here, just see the regularizer term. I'm just writing it. If you see the our regularizer term here, regularizer term means what? Here our regularizer term is norm of w by 2 means what? This one is 1 by our margin, that is this is our inverse of our margin. Okay, so if you just remember this thing, if you just remember this thing in logistic loss or any optimal problem, what will you do it there? In any optimal equations, we are going to minimize what? We are going to minimize our loss, plus we are controlling our regularizer term by some the parameters. So some parameters lambda we are using by lambda and to control hyperparameter to control our regularizer. This is the this thing, these situations we have seen in logistic regressions as well as in linear regressions, in KNN, in neighbor base, everywhere we are seeing this kind of equation. Also here, if you see this thing here, also we can see this one. Just we are interpreted this thing in different directions. In logistic regressions, we have see that our regularizer term, our loss function, we interpreted in different directions. Here we have seen that we are in another way, we are also interpreted our regularizer term, hyperparameter, loss function. So this is the main beauty of our mathematics. Our target, our always is same, but we are coming to this target in different directions, but we are reaching our goal in the same. So our main aim is to minimize the error. We have to maximize our classified point, minimize our misclassified point. Okay. And this here C is our hyperparameter, and we also see that C is always positive. Because for every hyperparameter, C is always positive. C is positive. Now, what will be the relations of the C to these objective functions? Now, just see the objective one. Just see the relations of the. If we increase the value of C, then what happen? And if we decrease the value of the C, then what happen? Just see this thing. If we just increase the value of C, then if we increase the value of the C, then what happen? Then we are giving the more importance from this part, loss function. If we are giving the more importance from this loss functions, means we are more minimize. We are going to more minimize this loss function. If we are going to more minimize this loss function, then what? It's just simple. Just if we taking out the constant C outside of this thing, then we are going to more importance of the minimizations of the average distances. Then if we giving the more importance from this part, actually then we are going to make our model better and better. We are going to make our misclassified point tends to 0. We are going to make our model as correct as possible. Okay, so in such situations our model will be will make less mistakes. So in such situations our model will be high variance model. Okay, so if we are increase the value of C, then the tendency to make mistakes on our training data set, that is dtrain, will decrease. This implies we are making the model a high variance model. We are making our model a high variance model. Okay, I think. Similarly, if we write this thing in, if we decrease the value of c, then what happens? If we decrease the value of c, then we are going to zero this term, then this term will be disappear from our equations. If we are just decrease the value, then we are then we are more prone to neglect this value. If we are more prone to neglect this value, means we are not considering our misclassified data sets. Okay, if we are not considering our misclassified data sets, then we are facing a bias problem. Okay, then we are making our model more biased model. Then in such situations, we are making our model high bias model. Okay, or another language, we are going to our model a underfit model. We are going to make our model underfit model, and here for high variance model, we are going to make model our overfit model. So we have to choose the c, this parameter, this hyperparameter c value in such a way our model is not much overfit as well as our is not much underfit. So this is the main relations of the hyperparameter to training this model. And one thing at the end of this lecture, we are just taking one thing. If you see the if you just sklearn, if you just see remember the sklearn library in logistic regressions, then there we have taken the hyperparameter c. Okay, then we are taking in logistic regressions, we are taking the hyperparameter c, and c is simply 1 by lambda. In logistic regressions in sklearn, you have not taken the hyperparameter lambda. In sklearn GPS sklearn, we there sklearn in logistic regressions hyperparameter is c. There we have not taken the hyperparameter lambda, but both are the same thing, just proportional to each other, just one is inverse to one another's. So because of this thing, because of this concept, because of this thing, okay, so because of this thing, here we have taken in logistic regression the hyperparameter c. Okay, I think clear. And one thing, just before closing this lecture, I'm just I want to remember you one thing. In logistic regression, you see that if we our decrease the value of lambda, if we our you remember thing, if we our decrease the value of c lambda, then in logistic regressions our model going to overfit. If we are going to increase the value of lambda, then in logistic regressions our model is going to underfit. So because of this thing, because c is inverse to our lambda. Okay, I think all the concept of submargins are clear now. If you have any problem, comment below, or please I request you, if you don't understand till now, please revisit this lecture. If after revisiting this lecture, if you have not clear this concept, please comment below. I'm again trying to taking this lecture. Okay, thank you.